Hello, everyone. So that's the topic for today, PlanetScale, how we do unlimited scaling for MySQL. So we'll start with what PlanetScale is and what we do, and then we'll talk about Vitess, which is the core technology that PlanetScale is built around, and then talk a little bit about what makes this whole system run, what makes it tick, and then I'll do a couple of short demos. I'm an engineer at PlanetScale. I'm one of the early engineers. I've been there for about 7 years, so pretty much from the beginning of PlanetScale. And I lead the engineering team for Vitess. And in the Vitess open source community, I'm also the technical lead for the project. PlanetScale is a MySQL compatible database as a service platform that was built for scale. It was founded in 2018 by the co-creators of Vitess. For people who don't know what Vitess is, we'll get to it in a bit. Based on the technology that scaled YouTube, PlanetScale offers reduced downtime, no maintenance windows, backups are automated, failure detection and recovery is automated, high availability, near unlimited connections. We also offer non-blocking schema changes, vertical and horizontal sharding, and multi-region support. Some of the companies that are running on PlanetScale are these logos: Attentive, Intercom, MyFitnessPal, Block. How is that working for them? Let's hear from a few of these companies. I won't overdo the testimonials, but I just wanted to share a couple of them. So from Attentive, the CTO says, PlanetScale has 3 things that matter as an engineering leader: a system that can be trusted, a cost structure that scales, and a boon to the team's overall effectiveness. And the reason for this is that PlanetScale does the database management so that engineering teams can focus on product development. From MyFitnessPal, databases are hard. Probably everyone agrees. And we would rather PlanetScale manage them. So engineering teams at MyFitnessPal can focus on helping their customers meet their health and fitness goals and not worry about the database servers. Let's talk a little bit about Vitess now. Vitess is a MySQL-compatible, horizontally scalable, cloud-native, distributed database system. A lot of buzzwords. Vitess was started at YouTube in 2010, and the reason Vitess was started is because YouTube was having problems on a daily basis. YouTube was running on a monolithic MySQL database, and they were growing so fast that they were simply not able to keep up with the growth in data volume, but also the growth in traffic. Vitess was donated to CNCF, Cloud Native Computing Foundation, in 2018, and it graduated in 2019. It was open source for several years before that, so Google/YouTube open sourced it back in 2015, and other companies started using Vitess in their large-scale MySQL deployments starting in around 2016. It's completely open source, Apache 2.0 license, and we have contributors from 100 plus companies, and many of them run Vitess in production themselves. Some of the big names that run Vitess in production are GitHub, Slack, HubSpot, Shopify. For people who use GitHub for their daily development, every issue, every pull request lives in Vitess, served by Vitess. Slack, a lot of people use Slack for workplace communications, and every Slack message is going through Vitess. So why was Vitess even created? Vitess was created because of all the problems that people were running into with single node MySQL. As data grows, so as data went into terabytes, people had issues with backup and restore times. They had problems recovering from failures. They were experiencing write contention on their primary database, deadlocks. They were hitting limits on network bandwidth for I/O. But also, people weren't able to buy their way out of this problem because there was a limit to the biggest machine they could buy, how much money they were able to spend buying hardware to just buy their way out of this problem. The other thing people were hitting were problems with having too many connections, because each connection is a separate thread in MySQL, and that is relatively heavyweight. Also, schema changes. Once your tables become very large, schema changes can become extremely slow and end up being blocking, so that no one is able to write any data to those tables while a schema change is in flight. So these are all the problems that the community was experiencing, and a lot of these problems over time, because now we are talking about 15 years ago, over time there have been various open source solutions, community-driven open source solutions for these problems. But also MySQL itself natively has solved many of these. So the way Vitess solved all of these problems was first by sharding. What sharding did was that it just brought down the size of each individual database server so that things became much more manageable. You could also split connections across multiple servers so that you were not running out of memory or experiencing so much contention on each server. In the Vitess architecture, every shard runs primary replica clusters. Typically, at least 2 replicas, could be higher. Reads can be served by replicas, and reads can be scaled by adding more replicas. Vitess also does connection pooling. What this does is that from the application layer, you can have hundreds of thousands of connections, which on the back end, MySQLs end up being maybe a few hundreds, because connections can be shared because not every application session is active all the time. Vitess also has automated failure detection and recovery for the primary servers of each shard, and it provides background schema changes with seamless cutover. Now, the way Vitess has solved these problems actually leads to some other problems. So you start serving queries from replicas, then you have to start dealing with replication lag. And you can mitigate this by using parallel replication workers, but also by throttling some workloads. The other thing that happens when you start serving reads from replicas is that you have eventual consistency. So the data that you're reading from a replica is not guaranteed to be completely up to date with what was written to the primary. And to solve this, you have to read from the primary. But people have developed various strategies to deal with this. For instance, at YouTube, what they did was, if someone wrote from their session to a particular table, let's say a user is updating their profile, then the subsequent reads would go to the primary instead of going to replicas. GitHub solves this a different way. What they do is that they set a timer and they say, in a session that is doing a write for the next n seconds, maybe 60 seconds, all reads will happen from the primary instead of going to the replica. So there are solutions to these things as well. Going back to PlanetScale, PlanetScale is built around Vitess, but it is more than Vitess, because it takes the primitives that Vitess provides and provides additional usability features to people who want PlanetScale to run their databases, for people who just want a database that works and is managed by someone else. So PlanetScale has schema branching, which is like Git. You can take your main production branch and create a copy of that schema in a branch, make your schema changes, and then merge them. This is just like merging a pull request or a merge request. And you will see a diff, and the merge happens in the background, and you can schedule when the merge completes, or You can let it run at its own pace and complete whenever it does. This can be coordinated with code changes so that if you're adding a new column only after the new column has been merged into your main production database, you deploy code that uses it. If you're renaming a column, you'll have to do it in 2 steps, things like that. PlanetScale offers backups and restores, and backups are scheduled automatically. There is a default backup schedule, and people can add additional backup schedules if they want to. These backups can be restored to new databases. We also have regional replicas. So applications these days are worldwide, and they are deployed in different regions, but the primary for a particular database obviously lives in one region. But we can deploy replicas in different regions for applications to read from and serve queries. We have query insights. This is actually a really cool feature that I'm going to demo. And as part of query insights, we can also do schema recommendations. Introspect the schema, look at how it's being used, look at the query patterns, and make recommendations to how it can be improved. We offer single sign-on so that enterprises can deploy their single sign-on solution, and people don't have to remember a new username, password for their PlanetScale account. There is PlanetScale Managed, where people can run in their own cloud account and use their cloud discounts. I should mention that PlanetScale only runs in the cloud. There is no on-prem solution. And we also offer Metal, which is instance storage versus cloud storage. Cloud storage is kind of slow and leads to increased latency for queries, and instance storage actually solves that problem. So how do we do this? How did PlanetScale build everything that we built? There are some foundational technologies that we rely on. First of all, MySQL, because PlanetScale is MySQL compatible, and it's a solution for people who want to run MySQL. And then Vitess, which allows us to scale, but also allows us to manage everything that needs to be managed around the MySQL instances. A big part of managing the databases at PlanetScale is actually Kubernetes. Because we are running thousands and thousands of processes, thousands of MySQL servers, MySQL processes, it's actually not possible for an infrastructure team of 10 people or less to manage all those servers. So everything is virtualized, everything is in the cloud, everything is a container, everything is running in a pod, and Kubernetes allows us to do this. But we don't just use Kubernetes, we've actually built a Kubernetes operator which manages all of these things. We have built a 3-way merge for schema changes similar to Git merge, and there is a patent on it, and this is the secret sauce behind our Git-like schema change flow. And then we use a lot of third-party tools to enable what we do, because there are things that other people have done well, which we should reuse. There is no need to reinvent everything. And a lot of it has to do with Kubernetes. In the Kubernetes ecosystem, there are a lot of tools, and we use a lot of them. These are just a few examples. We use Carpenter in order to do node provisioning. So we have security requirements, because of which we cannot keep a node running continuously for more than 30 days. We have to apply OS updates and security patches, and we use Carpenter to do that on AWS and Luna to do that on GCP. And we use Kafka to power our query insights. Okay, let's go to the demo. I have 2 demos. The first one is a database that is actually running in production. So for Vitess, we have a benchmarking system, and we have a benchmarking website. And this website actually stores all of the data that is shown on the website in a PlanetScale database. So Vitess benchmarking powered by PlanetScale, powered by Vitess. Okay, I hope that's readable. So here we have a database which is called Are We Fast Yet? Because that's what we call our benchmarking system. And the thing you're seeing here is the cluster diagram. So Vitess has a proxy layer called VT gates, and this is showing us that we've deployed 3 VT gates. We typically deploy them in 3 availability zones or zones. So availability zone A, B, C. So there's 3 of them, and this proxy layer receives all the queries and forwards them to the backend. And behind that, we have a MySQL cluster with 1 primary and 2 replicas. On this view, we can see an overview of the database. We can see that there are 7 tables. There are 2 branches. I'll talk about what branches are in a bit. There are no deploy requests, but we'll create one. There are no anomalies. So we are doing anomaly detection, but in this particular production database, there are no anomalies right now. There are some schema recommendations. We'll see what those are. We can see that the backup is scheduled to run again in about 10 hours, and we can see what our storage is. And this database is about 360 gig. All right, so let's look at query insights next. So here we can see the query latency and a bunch of other things. So here are all the queries that we captured in the last approximately 24 hours, and this time is in UTC. I didn't change my time zone. It's UTC. So these are sorted right now by total time, but I can change them to sort by latency, and we can see which is the query that has the highest P50 latency or the highest P99 latency, and then we can actually drill into that to see why is this query so slow. And somehow there was one point in time where this query was actually quite slow. But we can also see what are the errors that it received. And there is an error, out of sort memory. Consider increasing server sort buffer size. So this view actually shows us quite a lot of useful information about how the application is using the database, how the queries are performing. Now, let's look at what the application is recommending that we do with this database. Okay, so first of all, it says, there are these unused tables, let's drop them. And that's about it. Those are the recommendations. But there are some closed recommendations. So we actually recommended that we should add a new index, IDX execution on source, on the table called execution. So let's go back to insights and, oh yes. So let's look again at this slow query and look at indexes. So this is actually saying that there are no indexes being used for this query. So clearly, it's not a great query. So starting from here, what an application developer would do is to try and figure out whether adding an index to this query would help, experiment with it, and maybe choose an index. It helps or it doesn't help, and then that will be visible in this graph because we'll annotate insights with any schema changes, including index changes that are tried out. So let me go back to the dashboard, and I'll actually show you how we do schema changes. So I've already created this branch called add description to metrics. So I took one of the tables. Let me show you the tables. All right, we have 7 tables: execution, macro benchmark results, blah, blah, blah. So let's look at the metrics table. This is a simple table. There's an ID, there's an execution UUID. We are running benchmarks, and each run is an execution, and it has a unique identifier. And there's a name and a value for the metrics that we are capturing out of each benchmark. So I said, OK, let's try to do a schema change. And what we will do is we will actually add a column called description to this metrics table. So I've already done that on this branch. So similar to how you would do a git pull request or merge request, you take your production branch, you create a branch out of it, like a development branch, and you make the schema change on it. So now that we have the schema change, we can actually create a deploy request. All right, so I've opened a deploy request, and it says instantly deployable. So the schema change mechanism in Vitess is inspired by a lot of the open source tools that came before us. For example, Ghost, which is GitHub's online schema change tool, PTOSC, Percona tools, Facebook OSC, and prior to that, there were other tools as well. But what we've also done is that we have kept up with improvements in MySQL itself. So when MySQL introduced instant DDL, we said some changes are instantly deployable, and for those, we will actually do an instant deployment. So I can do deploy changes instantly and run it. And it should be done soon. OK, instant deployment completed successfully. So I'll go back to our dashboard and go back to the tables and look at the table definition. And you can see that the description column shows up, and it can be used. So on this database, this was the demo I wanted to show. But we'll move on to another database, which is actually a test database. This is a production database. So some of the things that I want to show, I don't want to do on a production database. But we'll do it on a test database. So here's another database that one of my team members created for me, and he thought it would be funny to call it GPT and create tables called chats and chat responses. So if we look at the tables here, that's what we have. We have users, we have chats, we have chat responses. And we should be able to see how much storage is being used on the dashboard. OK, so we don't have much data here. This is like 592 kilobytes, half a meg, very, very small database. But we can use it to do a resharding. So while Vitess is not the only solution that solves many of the problems we talked about, sharding is one thing that Vitess does extremely well, and almost no one else in the MySQL ecosystem has nailed it. So that's what I want to show right now. All right, so in this database, we have 3 tables: users, chats, and chat responses. Let's imagine for a moment that in each chat, there are so many responses that this table is growing very big, and we want to shard it. Typically, what you would do with Vitess is that you would first do what's called a vertical resharding. You will say, oh, this table is too big. Let me move it to a different server. That will buy me some time. It's still too big. Let me now split it into multiple shards. But you can do this entire operation in one step and say, I'll go from an unsharded database to a sharded database, and I'll just move this one table. So what I'm going to do is to create a workflow to do that. So our source is the current database, and we have another database where we will copy this. And let's validate, and it's going to be split into 2 shards. So let's validate this workflow. Everything is good. Let's create the workflow. Oops, we need a name. Demo. Let's see how long that takes. there are about, I don't know, 1,000 or 10,000 rows. 1,000 rows. So the way resharding works in Vitess is that there is a copy phase and a catch-up phase. So first, we will take a snapshot and copy over all the rows that we can. And in the meantime, bin logs are accumulating with changes to the table. And we will pause the copy and use the bin logs to catch up to any changes that happen to the rows that have already been copied. And then we go back and forth between this copy and catch up until we have completely replicated the source to the target. So this didn't take very long. So what we will do is we will actually just switch all traffic. So when you're doing something like resharding on a live production system, you really cannot afford to take any downtime. And Vitess actually provides near zero downtime cutovers for resharding workflows. And the way we do it is that we temporarily pause writes on the source. It's a production system. We pause writes, but we buffer the queries. So we actually hold them back. And then we reconfigure the metadata so that everything will start going to the target. And then we release those queries so that they start going to the target. And typically, this whole process completes under 30 seconds, even on a very heavily loaded production system. So we'll just do switch traffic. And in this case, it's instant because I'm not actually running any traffic to this database, and we can complete the workflow. So we can actually go back to the dashboard and look at, cluster configuration. PS chats is where we copied over the data. And it says this table contains 2 tables. This key space contains 2 tables. So clearly that information is out of date. Anyhow, so that's the other demo. And let's go back to the slides. Okay, these are just the screenshots I captured in case the demo didn't work for instant deployments, index usage, and schema recommendations. We have resources on the Vitess website and the PlanetScale website. We have a bunch of case studies. So some of the companies I named that I did not quote from have actually blogged on their own websites about how PlanetScale is helping them. And that's everything.